So I have started my PhD at the CCRC in March. So my proposal focuses on the study of the Ross model gyres using Access 1.2. And my supervisor is Matt England. What I'm going to show here are some preliminary results and rough results because I have started a couple of months ago, but yeah. So first, a little bit of background on these gyres. They are one of the dominant features of the circulation south of the ACC. They are both cyclonic gyres, predominantly wind-driven, and to some extent they are topographically steep. I say predominantly wind-driven because buoyancy could be playing a role here, and because they are one of the southernmost open ocean reaches in the world, they are connected to deep water formation and forward heat transport. However, despite their importance, they are very undersampled. There are only a handful of hydrographic sections here, and they are very sparse in time and space, with a very strong bias towards the summer month because of the obvious experimental difficulties in this region. Sorry about the interference. It's my microphone in the computer. It doesn't work well. Yeah, so there are not many Argo flows here compared to other regions also, and this has been improving in the past few years though. Because of the extensive sea ice cover in winter also, radar altimetry is somewhat limited, even though there are some new methods that have been getting around this limitation. So because of all this, getting a very thorough and comprehensive description of these gyres and their variability in long timescales, using observations alone is not possible as well. This is why using Access 1.2 to describe them could prove to be very useful. Well, so for now, what the Waddell transport has been estimated to be in between 30 and 100 sled trips, and the Ross transport has been estimated to be roughly half of that of the Waddell's. This is a wide range in transport, and this is attributed to the very different methodologies that past studies have used. The gyres both present a lot of variability in the seasonal timescales. The gyres are stronger during winter and weaker during summer, and there are some recent studies that relate the variability to climate modes such as SOSAM and the Amundsen Stilo. So with all this in mind, what I'm trying to do at the moment is study how the gyres look in Access 1.2 and trying to assess how the model reproduces observed features, how well the model works in the future. So what I'm going to use is the 3 resolutions available of the model. I'm going to use the interannual forcing experiment, which is forced with the JRA 55 atmospheric fields. And I'm going to use the entire period available, which is for the 1 1/4 resolutions starting from 1958. And for the 1/10, the years available start from 1985. And in the next few slides, I'm going to talk a lot about the barotropic stream function, which is defined as the meridional integral of the zonal depth integrated transport, starting from the Antarctica. So yeah, so a couple of results first. These are the mean fields in the Waddell region of the barotropic stream function. Bear in mind again that the difference among the resolutions could be attributed to the fact that I've constructed these fields using the entire period, and the 1/10 degree starts from 1985, so the period is a little bit different. What you can see is that the circulation in the 1 1/4 resolutions is similar in structure, with a double lobe present with western lobe and eastern lobe in both resolutions. This is an observed feature. This is something that has been reported in previous studies. But this double lobe is not as clear in the 1/10. Here it is hinted, but the eastern lobe seems to be more displaced towards the center. You can also see that the intensity and the area of the gyre increases with resolution, and the flow becomes more unstable. Yeah, so when you go to the mean fields for the Ross gyre, you don't see as much seasonal variation. seasonal variation among resolutions, it is clear that the 1 degree presents the weakest Gaia and smaller Gaia, but the other two resolutions look very similar. What you can see also is that the Gaia seems to be extending further to the west, and this could be related to deep water export from the Ross Sea, but I have not looked into that yet. So in order to look at the seasonal differences, I've made the mean fields for the summer and winter months, using again the entire available period. What you can see on the left column is summer, top for 1 degree, middle for 1/4, and bottom for the 1/10. On the center column, the winter fields, and on the right you can see the different summer minus winter. So because the stream function in this region is negative, a positive difference means a stronger Gaia during winter. And again, the fields for the 1 and the 1/4 resolutions look very similar, with a weaker Gaia during summer, stronger during winter. The double lobe circulation structure seems to be present in all but the summer fields of the 1 degree. And the region of highest seasonal difference is the eastern lobe. On the 1/10, again, you can see a Gaia which seems to be more displaced towards the center, but the seasonal differences maximize on what looks to be the western and eastern lobe, which I think is interesting. And remember that more or less approximately the seasonal differences are around 20 spectrums. When you go to the Ross seasonal fields, again, you don't see much difference among resolutions, and that the seasonal differences are around 10 spectrums, which is half of that of what was for the Waddell. So to keep looking at this Gaia's transport and its variability, I've constructed an estimate of the Gaia strength, which I defined as the regional minimum of the barotropic stream function, and with that value you can construct a time series. So this is an estimate. It can be that this is not the best methodology because these Gaias vary in space in the structure. And with that time series, I could construct an annual cycle, which is what I show here for the entire period again. And on the left panel, which is for the annual cycle for the Waddell, what you can see is the seasonal cycle that I've described previously, which consists of winter intensification and the summer weakening of the Gaia. The cycle looks the same looks similar in between resolutions. And you can see that the seasonal difference is of around 20 spectrums, a little bit less for the 1 degree. I think that the Ross cycle, which you can see on the right, is more interesting to look at because here winter does not seem to be the more intense Gaia, but you can see that there is a hint of a double peak. The Gaia seems to be more intense during April and then during August, September. And another interesting thing is that the Gaia goes through a very abrupt spin-up during the months of February, March, and April. So the Gaia spins up very rapidly and then spins down slowly during a lot of months. So perhaps this can be related to the fact that the Gaia responds fastly to the wind pulsing that changes during winter, and then this influence becomes dampened by sea ice cover. But this is again something that I should look into. So just to show you, this is the Gaia strength time series that I built, with which I constructed the annual cycle. And there are two interesting things. The thin line is the monthly values, and the thick line is the 12-month running mean. And there are two things that I think are interesting to see here. Is that first, the values for the transport fit within the range that is reported in past works based on observations. So that means for the Waddell in between 30 and 100 spectrums, and for the Ross in between 8 and 50. And another interesting thing is that the variability seems to be in phase, which speaks of the extent of the influence of the pulsing in these Gaias, which is the same for the 3 experiments, which is JRA 55. Yeah, so these are the results I have for now, and there are lots of future work and ideas to do here. And for now, what I'm going to do is to continue describing these gyres as they look in the interanual pulsing experiments. So looking at their mean characteristics and their seasonal and interanual variability and how this relates to different Feynman modes, and evaluate how well the model performs in reproducing the observed characteristics. So where are we reproducing what's observed and where we're not. A little bit into the future, I'd like to explore the wind and buoyancy forcing mechanisms using the same interanual forcing runs, and hopefully plan and run some experiments of my own. And a little bit more into the future, I'd like to investigate the role of these gyres in heat transport and deep water formation, and how would this be related to climate change. Yeah, so thank you.